Hi folks, welcome to the Algebra review for the Math SL exams. Basically in this section you'll be looking at arithmetic sequences in series, geometric sequences in series, logarithms, and binomial expansions. This is not endorsed or produced by the IB, it's just a little review that I made for my students in PEI Canada. You can print off the notes, just follow the link that's below, and you might find the most useful thing to be to print off those notes, work through the solutions, and then use the presentation to check your work. There are often a lot of different ways to solve a particular problem, so if you have a different way that you've been taught, perfect. Please use that. Okay, arithmetic sequences are sequences that have a common difference, which means they go up or down by a fixed amount through addition. So the sequence 2, 3, 4, 5 would be a pretty straightforward arithmetic sequence. It's got a common difference of 1. If I wrote it 5, 4, 3, 2, etc., then you're looking at still an arithmetic sequence, but here the difference has changed. The common difference would now be -1. The common difference is found by taking the n plus 1th term and subtracting the nth term, or in simplest language, the second term minus the first. The nth term of an arithmetic sequence is given by this formula right here, which is in your formula booklet. And the sum of the first n terms in an arithmetic series is given by these two formulas. So there are different formulas for it. You're going to choose which one you're going to use based on what you know. So this one over here is good if you know n, the first term, and the last term. This one over here is great if you know n, the number of terms, the first term, and the common difference. Geometric sequences have a common ratio. That means they increase or decrease by multiplication by a fixed amount. And that fixed amount is called that common ratio. It's given by the second term divided by the first, or generally the n plus 1th term divided by the nth term. So if I have a sequence that goes 3, 12, 48, it seems like I'm going up through multiplication here. The common ratio would be 4, which I could find by 12 divided by 3 gives me 4. And I can verify because the third term divided by the second is also 4, or 48 divided by 12 is 4. So the common ratio in that case would be 4. Now let's consider a geometric sequence that goes, I don't know, say the other way around, 48, 12, 3. Here you might be tempted to say, I'm dividing by 4 every time. But common ratios need to be framed in terms of multiplication. So instead of saying I'm dividing by 4, let's say I'm multiplying by a quarter. And that could be shown by second term divided by first term, which is a quarter, or 0.25. And verified by third term divided by second. 3 over 12, that's still a quarter. Okay? So we're showing here that it's a ratio and that it's common. It stays the same throughout the sequence. The nth term is given by this statement here. First term times the common ratio to the power of n minus 1. The sum of the first n terms is given by this statement. And sometimes geometric series have an infinite sum. So if they go on forever and ever, they're actually going to converge on a number. And that happens if your common ratio is between -1 and 1. And that sum is given by u1 over 1 minus r. Okay, you could also call it negative u1 over r minus 1. That would also work out. And there is also another formula that you could use for the Sn, which is in your formula booklet. Okay, arithmetic sequence. Let's take a look at a fairly straightforward problem here. Has a 20th term of 62, and the sum of the first 20 terms is 670. Find the value of u1 and the value of d. Well, in both these cases here, we're talking about n being 20. So essentially, we know the 20th term, the sum of the first 20 terms, and what n is. Let's see if there's a formula for sequences in series for arithmetic situations that uses those bits of information. So we know n. Yeah, that's good. I know Sn, and I know the nth term. This formula right here seems like it would work out well for us. We could solve for u1 because there's only one unknown left. But there are other ways of approaching this. I think this is probably the fastest one. Not n over 20, n over 2. u1 plus un. Okay, substitute in what we know. Sum of the first 20 terms is 670. N is 20. u1 is unknown, and un, or the 20th term in this case, is 62. 20 over 2 is 10 times u1, and also 10 times 62, which would be 620. We'll solve here. We'll get 50 equals 10 times u1, or u1 equals 5. Great. We've found the value of u1. Now we want to find the value of d. We could use either the Sn formula that has d in it, which would be this green one up here, or we could use our un formula. Well, we definitely have to use a formula that comes from arithmetic sequences and series, not geometric. Okay, so I'll take a look at the rest of this. un equals u1 plus n minus 1 times d. Plug in what I know. Un, the 20th term, is 62. u1 I know is 5 now. N minus 1, I'm talking about 20 minus 1, because 20 was our n. So this will be 19. Solve, and I get 57 equals 19d, or d equals 3. So I'm just cataloging what I know in these cases and plugging in to a formula that will allow me to solve the question that's being asked, namely find u1 and d in this case. Let's take a look at a geometric sequence that has u1 of 2 and a common ratio of 3. We want to find out which term number will be the first to exceed 1,000,000. Okay, so that means we're going to use our geometric sequence formula. un equals u1 times r to the n minus 1. Let's plug in what we know here. We know that our u1 is 2, that our common ratio is 3. We're looking for the term number, which would be n. And actually, we want that value to exceed 1,000,000. Okay, so if I read this instead of from left to right, from right to left, it's saying 2 times 3 to the n minus 1 is greater than 1,000,000. Now, we could solve a corresponding equation. Okay, and there are a bunch of ways to solve that. You can, first of all, you can divide by 2 and then use logs. Probably the most straightforward approach. Okay, take the log, either base 10 or natural log of both sides. I'm going to take base 10, but it doesn't matter. Bring down my n minus 1, my exponent, as I do it. And then divide both sides by log 3. My whole goal here is to isolate n. Okay, pull up my calculator. Log of 500,000. Make sure I close my brackets. Divided by log 3 equals 11.94. And that would be what n minus 1 is. So n itself is going to be 12.94. Just add 1 to each side. There is no 12.94th term. So we have to say here that it's going to be, since this is a geometric sequence that grows, it's got a common ratio greater than 1, we're going to be looking at the next term, the 13th term. Some other approaches to solving this might involve using your GDC to solve, say, this equation. Okay, so you could say that y1 is going to be 2 times 3 to the n minus 1. I'm going to put that in my GDC. 2 times 3 to the power of x minus 1. Okay. I could graph that. I know I want to see all the way up to what happens with a y value of 1,000,000, so I need to go up to at least 1,000,000. Maybe I'll go up a little higher. There we go. So somewhere around there, I can figure out where it's going to be 1,000,000. I could put y2 in of 1,000,000 and find that point of intersection. And it's going to give me x equals 12.94. If I instead went to the tables and looked at what's happening for my y1 curve, okay, I'll see that the 13th term is the first one to exceed 1,000,000. So I could show that U12 is from that little table 354,294, and U13 is 1,062,882. Whole bunch of different approaches here. I kind of like the logarithmic one best, but it's up to you. Okay, sigma notation. Sigma means the sum. And this is capital sigma, not to be confused with lowercase sigma, which we're using for standard deviation. So the expression that's given means the sum for p-values from 4 to 7. So all you really need to do here is substitute in those p-values. If I put in 4 for p, I'll get 4 squared, which is 16, minus 20, or negative 4. And then we're going to add on what we get when we put in 5 for p. 5 squared is 25 minus 20 gives us 5. Put in 6 for p. Okay, so this was p equals 4. This is p equals 5. P equals 6. If I put in 6 for p, I'll get 36 minus 20, which is 16. And if I put in 7 for p, I'm going to get 49 minus 20, which is 29. Okay, add them all up. And the sum is going to be 46. Now, often it's going to be really inconvenient for us to write out all of the terms. We'd have to write out the first few and just look for a pattern. In the first one, no problem to write out those 4 terms and add them up. Probably the simplest way to approach it. All right, let's see what happens here if we have from q equals 6 all the way up to 20, 3 times 2 to the power of q. So if I put in q equals 6, I know that 2 to the 6 is 64 times 3 is 192. Okay, plus what happens when I have q equals 7. 2 to the 7th is 128 times 3 is 384. Q equals 8. Okay, that would be 256 times 3, or 768. And this is going to be a pain to keep writing. Now let's see what we have here. 384 and 192. We seem to have doubled and then doubled again. This is a geometric series that we're showing here. So rather than write them all out and add them up, I can go to my geometric series formula. And this is the version of it I like to work with. Some people might use this one, which is also good. Makes no difference. Okay, substitute in what I know. Well, I want from the 6th to the 20th terms. That's actually 15 terms, so I'm looking for S15. The first term was 192. The common ratio, I'm going up by multiplying by 2's. So this will be 2 to the power of 15 minus 1 all over r minus 1. So 2 minus 1. I'll plug that into my GDC. 192, open brackets, 2 to the power of 15 minus 1, divided by I really shouldn't have to put in 2 minus 1 in my calculator, but I just want to show you to be careful of the brackets as you do it. Okay, and I should get 6,291,264. Plug them in carefully. All right, logarithms. If you've got the expression log base 2 of 1/8, it's asking you a question. It's saying, what power do you need to raise 2 to in order to get 1/8? So you know 2 to the power of 3 gives you 8, and a negative power flips it upside down so that you've got a fraction. So the power that you need to apply to 2 in order to get 1/8 must be a -3. Therefore, log base 2 of 1/8 is -3. It could also be written in exponential form. And in your formula booklet, you're given how to convert between the two, in case you forget. Okay, I think this is the way it's written. A to the x equals b can also be written as log base a of b equals x. That's from your formula booklet. You need to be able to change an equation from logarithmic to exponential form, and there I have it written using this fact. So, if I've got log base 3 of 20 equals x, I can convert that into exponential form. The base is 3, the exponent is x, and the result is 20. At this point, I can take the log of both sides, either base 10 or natural log. So, I can go log of 3 to the x equals log of 20. That lets me bring my x down. And I can divide both sides by log 3. We're just following the golden rule of equations here. Whatever you do to one side, you can also do to the other. So log of 20 divided by log of 3 can give us 2.73 to 3 sig figs. Okay. There's also a change of base rule, which we'll look at on the next page, that simplifies these types of questions. We could also check this. Okay, put it back in. Check whether 3 to the power of 2.73 really does give us 20. 3 to the power of 2.73. Yeah, it gives us 20 with a slight rounding error. If no base is shown on a log, the base is assumed to be 10. Natural logs have a base of e. Logs are great when you're solving equations where the variable's in the exponent. They let you bring it down using some of your log laws. So if I had this equation right here, 5 to the 2x minus 3 equals 4 times 10 to the negative 2. I think this actually does come from one of the old IB questions. My first inclination here would be to rewrite the scientific notation part as a decimal, though you can certainly deal with it in scientific notation. Alright, then we realize our variable is in the exponent. I'm going to need to take the log of both sides so that I can eventually bring that down. So log both sides of 5 to the 2x minus 3. And log of 0.04. I can now bring down my exponent all together. Need to put it in brackets. Equals log of 0.04. Okay. Divide both sides by log 5 to start isolating our x. So we'll get 2x minus 3 equals. I might be tempted to go to the calculator at this point rather than wait till the very end. Log of 0.04 divided by log of 5 gives us negative 2. That's nice and convenient. It's not always going to work out that nicely. Gives us 2x equals 1 or x equals a half. And we could go back and check that. Now, you might be saying, I had another way of doing it. Here would be an alternate approach. If you realize that 0.04 is the same as 1/25th, we could write it this way, which initially doesn't look like it's helping you out a whole lot. But then we say, okay, well, 1/25, that's 5 to the power of negative 2. I've got 5 to the 2x minus 3 equals 5 to the negative 2. When we have the same base on both sides, and we know that both sides must be equal, that means we must have the same exponents on both sides as well. So I can equate my exponents. 2x minus 3 must equal negative 2, which gives us 2x equals 1 or x equals a half. Didn't have to use my calculator at all to use that method. So if you can find a common base on both sides, the logs really aren't necessary. Let's take a look at our log laws. I didn't show any bases here, so they're assumed to be base 10. But they'll work for any base. So log of AB is the same as log A plus log B. Log of A over B is log A minus log B. And this one right here tells you that you can bring your exponent down. And that's what we've been doing in the last few questions. Okay, a few other little log facts here. This one's really important. Log base A of A is 1. So log base pi of pi is 1. Because it says, what power do you have to raise pi to in order to get pi? Log base root 7 of root 7 would also be 1. You can't take logs of 0 or a negative number. So log of negative 17, not possible. Okay, log equations. The way that I think of these is as falling into two types. Short log equations would be ones that only have a single logarithmic term in them. Okay, so this one from the last page where we said log base 3 of 20 equals x only had a single log in it. We could convert it to exponential form and then use our logs to solve. And then there are the types that I call long. They've got multiple logs. They're not more difficult, they just take a little longer to do. Convert to a single log of the same base on each side. At that point, just like we dropped the bases in the last question, you can drop the logs here. You can solve, and then you need to check, because you may end up with what's called extraneous solutions. Solutions that look like they work for the version of the equation that you're working with, but don't actually work in the original equation. So for this one down here, we've got two logs on the left and one log on the right. We can put these together. Two logs being added means that you multiply whatever you're taking the log of. So x times x is x squared. X times 1 is x. I put them together into a single log on the left, and I already have a single log on the right. Now I can drop my logs. Ooh, it's a quadratic. Factor and solve. What adds to 1 multiplies to negative 2. Oh, we can get plus 2 and negative 1, which gives us solutions of x equals negative 2 or x equals 1. Now we go back and see if either of those cause a problem. If I put in x equals negative 2 back here, I'll be taking the log of a negative number. That is not allowed. So this is an extraneous solution. It doesn't count for our final solution set. The x equals 1, no problems. Log of 1, I can do that. Log of 1 plus 1, or 2, I can do that. This is our solution. So we only have one solution here of x equals 1, even though it looked like we might have 2. Okay, recall that log base a of a is 1. This can be helpful in a long log equation where you have one term that doesn't have logs. So over here I have log base 3 of x minus 2 equals log base 3 of 4. How I would think of this is 2 times 1, negative 2 times 1, and another way of writing the number 1 is log base 3 of 3. Now I can move that 2 up on top of the 3 because it's really an exponent that used to live up here. So minus log base 3 of 3 squared, which I might just write as 9. And some people might have jumped to this step right off the bat. That's fine, because they knew 2 is the same as log base 3 of 9. Okay, then that's going to give me log base 3. I can put my logs together on the left-hand side. I'm subtracting logs. So I should get x over 9 equals log base 3 of 4. Drop my logs. X over 9 equals 4, which in turn gives us x equals 36. If I put that back in, I'd have no problems. Okay. An alternate approach for these kinds of questions, if that doesn't work well for you, would be to put all your logarithmic terms on one side and put your regular numbers on the other. So you'd have log base 3 of x. I'm going to move that log base 3 of 4 over by subtracting it from both sides. And I'm going to add 2 to both sides. So I've just rearranged it in this format. Okay, I can put these together as log base 3 of x over 4. And then treat it like one of those short logarithmic equations. Put it in exponential form. So I have a base of 3, a power of 2, and a result of x over 4. Gives me 9 equals x over 4, or still gives me x equals 36. Either approach would be fine. Change of base rule. Log base b of a is the same as log a over log b, or ln a over log b, or log with any base of a over log of that same base of b. So on the last slide, we had done this, log base 3 of 20. Change of base rule says that we should be able to do it as log 20 over log 3, which is what we ended up with, and we got 2.73. Or we should be able to do it as ln 20 over ln 3. I wonder if that works. Ln 20 divided by ln 3. Yep, works just as well. And if your calculator worked in different bases, you could do it in any number of base. So the IB sometimes finds these great ways of testing you about these questions without using your calculator at all and keeping it somewhat abstract. So this is a good case in point. Log base a of 2 is x. Log base a of 5 is y. Write the following in terms of x and y only. Now I know sometimes students will be inclined to try and solve for a. You can't do that, and that's not what the question's asking you for anyways. Just looking for an expression in terms of only x and y that represents log base a of 20. Let's think about log base a of 20. We can split it apart. 20 is 2 times 10, or 4 times 5. I'm going to go with the 2 times 10. So I could split it this way. That's going to be useful to me because this part right here is an x. But this part right here doesn't help me at all. Okay, so log base a of 2 plus log base a of 10. I could split some more, though. Log base a of 2. And then 10 is the same as 2 times 5. Ooh. So this means log base a of 2 is an x, plus another x, plus a y. And there'd be a lot of different ways that you could get there. You could have split it to start with as log base a of 4, plus log base a of 5. Said 4 is 2 to the power of 2, so this is really 2 times log base a of 2 plus log base a of 5. Still going to get you to 2x's plus a y. All right, here's where it gets kind of fun. Log base 5 of 2. If I wanted to do this in my calculator and just find what the value of that is, I'd probably go log of 2 divided by log of 5 using change of base rule. Oh, but but that's not what we're being asked for. Not the value of this, but how we could express it in terms of x and y. And here's the little trick. It doesn't have to be log base 10 that we're using. It could be log of any base. And what base do we want in this question? Bases of a. So log base a of 2 over log base a of 5, which is the same as x over y. Pretty sneaky. All right, last topic that's in this sort of mishmash that's called Topic 1 Algebra for the SL course. And that is binomial expansions. Okay, when you're expanding a binomial, your coefficients, or your first set of coefficients, come from Pascal's triangle. Now, I know a lot of people put the first row here of a 1, which would come from 0C0, or 0, 0. I like to lop it off just for the sake of binomial expansions, though I will agree it does not look like a triangle with that first row. So you may have to reconcile the way that you've been taught with having either a first row or not. Or you can think of this as coming from combinations. Okay, and if we were to write Pascal's triangle in terms of combinations and start at this row with 2 entries, this would come from 1C0, then 1C1. The next row would be 2C0, 2C1, 2C2. So Pascal's triangle gives you this nifty little way of finding combinations really easily. 4C0, 4C1, etc. 4C2, 4C3. And just as a point of interest, not that you're going to be responsible for this explicitly, but this is where NCR comes from. All right, so if we want to expand 2 minus x to the 4th, here's how I do it if I were going to actually write down the combinations that are going to be used. It's to the power of 4, so I'm going to need 4C0 as my first coefficient. I'm going to take the first term in the binomial and raise it to that highest power of 4. The negative x is going to be raised to the power of 0, so it's not going to show up at all. My next term will have a 4C1 for starters, and I might even just write in all the different initial coefficients. 4C1, 4C2, 4C3, and finally 4C4. Okay, I can't have a 4C5. Now, as I go across, initially I had 2 to the power of 4. Now I'm going to have 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, and finally 2 to the power of 0, which is just 1. I don't have to show it. See how the powers went down on this first coefficient, or this first term in the binomial, rather? Now we're going to take the second term, and its powers are going to go up. We're multiplying here, so this will be times negative x, times negative x squared, times negative x cubed, and finally times negative x to the 4th. So powers go down on the first term in the binomial, powers move upwards on the last term in the binomial. You may not have wanted to show this first step with the combinations. You might have gone straight to Pascal's triangle and said power of 4, that's the 4th row of the triangle if I write it without that first top number. Okay. So coefficients of, initial coefficients of 1, 4, 6, 4, 1. Or I could go to my GDC and get it to do 4C0 for me, etc. Okay, 2 to the 4th, I know is 16. Okay, this will be 2 to the 3rd, that's 8 times negative x. 2 squared is 4. I'm just working out each individual part here, working out the exponents and the combinations. Negative x cubed, and this will be x to the 4th. Okay, let's multiply. 1 times 16 is 16, minus 32x, plus 24x squared, okay, minus 8x cubed, and plus x to the 4th. There's the expansion. Alternately, we could have written out 2 minus x 4 times, used distributive property, really that's going to be unpleasant, and the likelihood of following it through without any errors is relatively low. So binomial expansion can really save us some time, and especially being able to use the triangle well. Hence, find the coefficient of x squared in this. Alright, notice the hence. It means using what we just found. So, 3x minus 1 times, oh, I already know what 2 minus x to the fourth is. It's this. Now, where am I going to get x squareds? Well, I'll get x squareds from the 3x part times the x term in here. And also from the negative 1 times the x squared term. So that's going to lead us to 3x times negative 32x is negative 96x squared. Negative 1 times 24 is negative 24x squared. I don't have to do the whole expansion to figure out what the coefficient of x squared is going to be. I could, but it would be a waste of time. And as you know, time's at a premium in these exams. Gives us negative 120 x squared. And sadly, and somewhat cheaply, that probably isn't going to get you full marks. You have to make sure that you answer the question that's being asked. It's only asking for the coefficient of x squared. So the coefficient is negative 120. Sometimes when we're looking for specific terms in our expansions, we'll want to look at patterns that appear on the variables. So let's take a look at this one. Find the constant term in the expansion of 2x squared minus 1 over x to the power of 6. There is a formula for finding a specific term in an expansion, but what I like to do is just write out the pattern, and everything sort of takes care of itself. So my first term would be a 6c0. It's got 2x squared all to the power of 6. My second term would be a 6c1. It would have 2x squared all to the power of 5, and now I'd have negative 1 over x. If I look at what's going on here, my first term is going to have an x squared to the 6th, or an x to the 12th. My second term will have an x to the 10th times negative 1 over x. In other words, it'll have an x to the 9th. That pattern of powers decreasing by 3 is going to continue. So my third term would give me an x to the 6th. My fourth is going to be an x to the power of 3. And my fifth will give me x to the power of 0. Which means a constant term. So this is the one that we want. Let's set it up. First term had 6c0, second had 6c1, third would have 6c2, fourth would have 6c3, fifth would have 6c4. And obviously you don't have to write out all this sort of rough work that I'm doing. It can be happening in your head. Okay, the first term had 2x squared to the power of 6, then we'll have 2x squared to the power of 5, then 2x squared to the power of 4 in the third term, to the power of 3 in the fourth term, and 2x squared all to the power of 2 in the fifth term. Our negative 1 over x makes its first appearance in the second term, and its powers will go up, so it'll be squared in the third term, raised to the power of 3 in the fourth term, and to the power of 4 in the fifth term. Okay, so from here, we can go to our calculator and find what 6c4 is, or we could use the triangle. Turns out to be 15. We'd have 2 squared, which is 4, times x to the fourth. And our last part would give us 1 over x to the fourth. Multiply those out, and you've got 60x to the fourth over x to the fourth. Oh my gosh, that really is a constant term. So we get a little bit of confirmation here that we've done the right thing. If you knew, if you were able to reason out that it's the fifth term, you could always have just used this little formula, the r plus 1th term in binomial expansion is nr, where n is the power. A is the first term from the binomial, and b is the second term. So for us, we would have used, if you had done it this way, we would use r equals 4, because we're looking for the fifth term. So the 4 plus 1th, or fifth term, would be, n would be 6. That's the power on our initial expression. A here, our first term in the binomial, would have been 2x squared. And b would have been negative 1 over x. Good luck, folks, on your Math SL exams, and tune in for another review.